Hello student, I Abhishek Vishal welcome you to on the lecture of op-amp based differentiator and integrator. In this lecture, we will discuss the another application of op-amp. We will cover the following topic: op-amp based differentiator and integrator. Here the first is definition of op-amp based differentiator. The second point is design of op-amp based differentiator circuit. The third is behavior of differentiator. The next is definition of operational amplifier based integrator. The definition of op-amp based differentiator and operational amplifier based differentiator is an electronic circuit that perform mathematical differentiation on input voltage signal. Differentiation is the context refer to the mathematical operation that calculate the rate of change of a function with respect to time. In electronics circuit, it means detecting rapid changes or spike in the input voltage signal and producing an output voltage proportional to the rate of change of input voltage. The op-amp differentiator circuit typically consists of operational amplifier, a resistor and a capacitor. In the input voltage is applied to the inverting terminal of the op-amp and the output voltage is taken from the output terminal of op-amp. The resistor is connected in series with the input voltage and the capacitor is connected in parallel with the feedback loop between the output terminal and the inverting terminal of the op-amp. When a rapidly changing input voltage signal is applied, the op-amp differentiator circuit respond to the rate of change of the input signal. The capacitor charges and discharges quickly, allowing the circuit to detect an output voltage pulse corresponding to rapid change in the input voltage. The mathematical expression for the output voltage V out of op-amp differentiator can be represented by V out is equal to minus R C into dV by dt, where V out is the output voltage across the capacitor. Next, V in is the input voltage applied to differentiator circuit, R is the resistance in ohm, C is the capacitance in farad, in dV by dt in represent the rate of change of input voltage with respect to time. The negative sign in the output voltage equation signifies a 180 degree phase difference between the input and output signal. Op-amp differentiator are commonly used in application where the detection of rapid changes or spike in an input signal is essential, such as in the pulse detection, the waveform shaping and high frequency signal analysis. Design of op-amp based differentiator circuit. The component required: first, operational amplifier. Choose a suitable general purpose op-amp like the LM741 or any other op-amp based on your requirement. Resistor: choose a resistor value according to the desired gain of the circuit. Capacitor, choose a capacitor value based on the desired frequency response. The circuit diagram is shown below. The op-amp based differentiator circuit consists of an op-amp, a resistor and a capacitor. Here the basic circuit diagram of differentiator. Op-amp differentiator circuit. In this circuit, V is the input voltage applied to the inverting terminal of the op-amp. V out is the output voltage taken from the output terminal of the op-amp. R is the resistor connected in series with the input voltage. C is the capacitor connected in parallel between the output and inverting terminal of the op-amp. The working principle is the most important concept is virtual short concept. The virtual short concept, in this concept, according to the virtual short, the voltage and the inverting terminal of op-amp is considered to be equal to the voltage at the non-inverting terminal. In this circuit, the non-inverting terminal is usually connected to ground. So, V plus is equal to 0. The differentiation process, when voltage signal V in is applied to the inverting terminal through a resistor R, the capacitor C charges and discharges based on the rate of change of input voltage. The output voltage V out is given by formula V out is equal to minus R C into dV by dt. In the negative sign indicates a 180 degree phase shift between the input and output signal. The frequency response. The frequency response of the differentiator is determined by the value of R and C. Lower value of R and higher value of C result in a higher cutoff frequency, allowing the circuit to respond to higher frequency component in the input signal. The steps to understanding the working. The first step is apply an input signal. Apply a varying input signal, that is V in, to the inverting terminal of the op-amp through the resistor. The output, measure the output voltage V out across the capacitor. Observe how the output voltage changes conquering the rate of change of the input voltage. Rapid change in the input signal will result in significant output voltage variation. The experiment with different frequency. Here we apply input signal with different frequency and amplitudes. Observe how the circuit respond to various frequency component, emphasizing the differentiation effect of the rapidly changing part of the input signal. The simulate the circuit. Simulate different input waveform and observe the corresponding output waveform to gain a deeper understanding of the circuit behavior. Analyzing the waveform of an op-amp based differentiator is essential to understand how the circuit respond to different input signal. Let us perform a detailed analysis of the waveform considering various input scenario. The first signal is step signal. Input signal, a step function, basically a sudden change in voltage. The behavior of differentiator: when a step input signal is applied, the differentiator respond by producing a spike in the output voltage. This spike occur due to the rapid change in the input voltage at the moment of step. The output waveform will be a short duration pulse representing the instantaneous change in the input waveform. In V in is equal to u t, where u t is the unit step function and output is minus R c into d v by d t. In R c, now the in R c, where differentiation of unit step function is delta function. So, output is R c into del d t. The next is sine wave input. Input signal is a sinusoidal waveform behavior. For a sine wave, the input, the differentiator produce an output that emphasize the high frequency component of sinusoidal signal. Output waveform will be a series of spike occurring at the zero crossing of the input sine wave. The amplitude of this spike is proportional to the rate of change of input signal. The waveform is V in is equal to a sine in the bracket 2 pi f t and output is cos 2 V out is equal to 2 pi r a C f cos 2 pi t, differentiated sine wave. The next is square wave input. Input signal, a square wave. The behavior of square wave is applied the differentiator amplifier, the edge of square wave producing a spike at the rising and falling edge. The output waveform will have sharp positive and negative spike corresponding to the rising. Here the result is V out is equal to minus 2 pi r a f into sine cos 2 pi f t. The next is ramp input. The input signal, a ramp function gradually increase or decrease voltage. For ramp input, the differentiator produce a linear increasing or decreasing output voltage. The output waveform will be straight line with a slope proportional to the amplitude of the ramp input. Waveform V in is equal to a into t, where it is a ramp function and output is V out is equal to minus R c, that is constant slope. The next is impulse input. Input signal, an impulse function or an instantaneous pulse. The behavior is circuit is when an impulse function is applied, the differentiator produce a spike in the output at the instant of the impulse. The output waveform will be a short duration pulse representing the differentiation of impulse function waveform, that is derivation of delta function. The next is noise input. Input signal, random noise or high frequency signal. For noisy input signal, the differentiator emphasize the high frequency component producing spike or pulse corresponding to rapid change in the input signal. The output waveform will contain erratic spike representing the rapid fluctuation in the input noise. The waveform is equal to noise, that is random signal, and the output is V out is equal to minus R C dV by dt. The result is differentiated noise signal. Here you have to note the some important points. First, the amplitude of the output spike is proportional to the rate of change of the input signal. Faster change in the input result is higher spike in the output. The output waveform experience a 180-degree phase shift compared to the input signal due to the inverting nature of differentiator. The bandwidth of the differentiator determine its ability to respond a high frequency components. A wider bandwidth allow the differentiator to capture rapid changes in the input signal. Here we need to careful selection of resistor R and capacitor. Value is crucial to achieving the desired differentiation behavior of the specific input signal. Different frequency component require different RC time constant for optimal differentiation. Analyzing the waveform help in understanding the response of an op-amp based differentiator under various input condition, enabling engineers to design circuit for specific application effectively. Now, we discuss the integrator. Here the definition of an operational amplifier based integrator. An operational amplifier based integrator is an electronic circuit that perform mathematical integration of an input voltage signal. Integration in this context refer to the mathematical operation that calculate the area under a curve of a function with respect to time. In the context of electronic circuit, it means accumulating the input voltage over time and producing an output voltage that represent the integral of input voltage. The op-amp integrator circuit typically consists of operational amplifier, a resistor R and a capacitor. The input voltage is applied to inverting terminal of the op-amp and output voltage is taken from the output terminal of the op-amp. The resistor is connected in series with the input voltage and the capacitor is connected in parallel with the feedback loop between the output terminal and the inverting terminal of the op-amp. When the input voltage is applied, the op-amp integrator the input signal by charging and discharging the capacitor. The output voltage across the capacitor represent the integral of the input voltage with respect to time. The integration process occur due to the relationship between voltage, current and time constant in RC, resistor capacitor circuit. The mathematical expression for the output voltage of op-amp integrator can be represented as the output voltage across the capacitor, that is V in is the input voltage applied to integrator circuit. R is the resistance in ohm, C is the capacitance in farad. T represent time. The negative sign in the output voltage equation signifies a 180-degree phase difference between the input and output signal. Op-amp integration find application in various fields including signal processing, waveform generation and analog computation, where the integration of input signal is required for specific function or application. Designing an op-amp based differentiator circuit involve selecting appropriate component and value of the operational amplifier, resistor and capacitor to achieve the desired differentiation behavior. Here a step by step guide to design the circuit. First, the component required. Operational amplifier. Choose a high gain general purpose op-amp like the LM74 or more modern equivalent with high slew rate for better performance. Resistor. Determine the resistance value based on the desired gain and frequency response. Capacitor. Determine the capacitance value based on the desired cutoff frequency. The design step. First, determine the desired cutoff frequency Fc. The cutoff frequency Fc define the frequency below which the output is approximately equal to input and above which the output start to the attenuate. Choose a cutoff frequency that suit the frequency range of the input signal. For example, if you want to differentiate signal up to 1 kilohertz, you might choose a cutoff frequency of 1 kilohertz. Calculate the capacitance, use the formula, that is 1 by 2 Fc is equal to 2 pi R C. Rearrange the formula where C is equal to 2 pi cutoff frequency into R. Plug the desired cutoff frequency and calculate the capacitance. Determine the gain bandwidth product of the op-amp. The gain bandwidth product define the maximum frequency at which the op-amp can operate with a specific gain. Choose an op-amp with gain bandwidth greater than the desired cutoff frequency, multiply by desired voltage gain into voltage gain bandwidth into voltage gain. Choose the suitable resistor. The resistor value can be chosen based on the gain required and the input impedance of the circuit connected to op-amp. The voltage gain AV of differentiator is given by. Choose an appropriate value for on the desire for resistor based on the desired gain and calculate R. Now, prepare the circuit. Connect the chosen resistor between the inverting input terminal and output of op-amp. Connect the capacitor between the inverting terminal and node where the input signal is applied, connecting to the non inverting terminal to the ground reference. Check the stability, noise consideration, ensure the circuit is stable by checking the phase margin and bandwidth of op-amp. Consider addition components like resistor, capacitor to stabilize the circuit if required, including filtering component if noise in the input signal is a concern. Apply the simulation test and test the circuit. Iterate and optimize, and remember to consider the factors such as noise, stability, frequency response during the design process for a reliable and accurate circuit. Now, here the some application of differentiator and integrator. Signal processing, differentiator use in FM modulator and demodulator to the recover the signal. It is used phase lock loop for frequency modulation, frequency analysis. Differentiator are utilized in frequency analysis application where the rate of change of signal need to be determined. The next is waveform shaping, pulse detection, medical instrumentation. Differentiator are employed in ultrasonic transducer circuit for producing signal from ultrasonic sensor. Now, the application of op-amp based integrator. The waveform integration. Integrator are used to integrate a signal over time, providing information about the area under the waveform. Frequency measurement. Integrator can measure the frequency of signal by integrating it and observing the output voltage, which is proportional to frequency. Voltage to frequency conversion. Integrator can convert a voltage signal to a frequency signal. Oscillator circuit. Integrator are used in oscillator circuit where the integrator of a square wave result in a triangle wave, which is then a feedback to create a stable oscillation. The next is ramp generation. Integrator are employed in ramp generator circuit used in application like sweep generator and time based generator in oscilloscope. The next is DC offset removal. The next is PID controller. Audio processing. Integrator are used in audio application for filtering and equalizing purpose. It is used also in voltage control oscilloscope for waveform shaping. These application shows the versatility of op-amp based differentiator and integrator circuit, making them fundamental building block in a wide range of electronic system. Thank you for watching this video.